In the last video, we looked at finding out the theoretical probability for different events. However, it's not always possible to get the theoretical probability. It might be too hard to calculate or to work out. So sometimes you have to do an experiment. When we do an experiment, it's important that we do it enough times to be accurate. The more times you do the experiment, or the more trials you conduct, the better your results will be. And I'll show that using a computer simulation. In this computer simulation, it's going to be looking for the event two tails when I toss two coins in the air. So here are the four things that could happen theoretically. I could get two tails, a tail and a head and a tail, or two heads. That means the probability of getting two tails is 1 out of 4. That's the theoretical probability. That's the same as 25%. So let's have a look what happens when the computer pretends to toss the coins and see how it happens, see what goes. I've got the computer to run the experiment twice. So on the left is the first experiment and on the right the second one. One of the things you'll notice that at the start, when not as many coins have been tossed, this one has almost 40% of them being two tails before it levels off at about 25%. In the second experiment, at the start, there was about 10% of the coins being two tails before it again levels off at 25%. It doesn't matter how many times you run the computer, the start can be up and down all over the place and very unreliable, but eventually it will settle down to 25%. And that's one of the key things about doing an experiment. The more trials you run, the more accurate your results will be at estimating the theoretical probability. So our experimental probability for this one is saying 26%. For this one, it's saying 24%. If I average those, I'd get 25%. If I let the computer run for longer, it eventually settled down at 25% for both of those. The longer you run it, the more accurate it is. So here's an example where someone's got a die, and it's got 6 numbers on it. 1, 2, 3, 4, 5, 6, like a normal die, but it's a biased die, which means they're not coming up the same way as a normal die. 1 chance in 6 for all of the different numbers. So allowing for the fact that there's not very many trials being done here, we're still going to be able to work out some, give an idea of the probabilities of different things happening. So let's do that. First of all, I need to add up the total number of the total frequency. So if I add up 2 plus 1 plus 2 plus 4 plus 6 plus 5, which is 20. So there were 20 trials run. Out of the 20 trials, 2 turned up as a number 1, 1 turned up as a 2, 2 turned up as a 3 on the die, etc. So let's have a look at the first example. How many trials were there? And the answer for that's 20. 20 trials were undertaken. How many 5s were there? Well, there were 6 of those because 6 times the number 5 was rolled. What is the relative frequency for each outcome written as a decimal? So starting with the first one, this is 2 out of 20, 1 out of 20, 2 out of 20 again, 4 out of 20, 6 out of 20, and 5 out of 20. If I change those into decimals, I'll get 0.1, I'll get 0.1 there as well, 0.05, 0.2, 0.3, and 0.25. If you're not good at changing decimals into fractions, just remember if you get your calculator and do 2 divided by 20, you'll get this number, 0.1. If I do 4 divided by 20, I'll get 0.2. If I add all these numbers up together, they add up to be 1. If I add up all these fractions together, I'll get 20 over 20, which is also 1. The reason they add up to 1 is because these are the only outcomes that can happen when you roll a die. So I'm certain one of those has to happen, so when you add them up, they have to add up to be 1.